Greetings to my seminar panels, Dr. Sofian and PM Dr. Zamri. My name is Mohamad Fariz bin Mohamad Fauzi, a final year student of Mechanical Engineering. In this presentation, I would like to present my final year project entitled The Development of Tethered Drone Station. To begin with, this presentation consists of 5 important parts, which are introduction, literature review, methodology, analysis, and conclusion. Fundamentally, a tethered drone is associated with the ground control system, which is known as its station. The drone is connected to the ground via tether, which is power supply located. As the drone flying away, the tethered system is required to feed a longer wire to the drone. This study is conducted to self-develop a suitable system for the wire control mechanism. Problem statement for this research is this research is conducted due to issue of wire management in the tethered drone station. Thus, we conducted as we want to develop an efficient method to manage the issues. The objective of this research are to determine the important parameter of the system, design and fabricate the prototype, and develop the traction system. Scope of study stated as shown in the slide. The development focused on retraction system application, which is feeding and retraction mechanism. SolidWorks software is used to sketch the design that able to work with maximum load applied. Next, the literature review. Articles that related to the research is referred to gain a better understanding of this topic. For the first article, the study is focused on method for correcting position of tethered drone. Next, the article is discussing about the producing power feeding tethered system. And lastly, the article is discussing on developing an autonomous power over tether system. We will move to the methodology part. Figures show the overall flowchart of this research. The fabricating of the prototype will begin with selecting material. For base station frame, we will use stainless steel square tube with plywood is attached on top of it. For spool part, we use 3D printing with filament is polylactic acid. Next, for the hardware of the system, there are 5 important components which are Arduino Uno, 12-volt battery, load cell, 12-volt DC motor, and jumper wire. This component will be integrated to create an automatic retraction system. Furthermore, there are 3 software that used in this research. First is Arduino IDE, which we to do the coding of the Arduino. Second, SolidWorks software, and finally is Ultimaker Cura for printing the part using 3D printing. We will move to the analysis part. Figure 5 shows the prototype that successfully been fabricated. As we can see, the load cell will be the input of the retraction system in figure 6. Mechanical evaluation is used to monitor the progress of the study. The evaluation will be focused on to identify the functionality of the retraction system that been developed. The evaluation aspect are source of power, load, sensor, type of tether, and rotation of motor. The progress indicate that the development is following the right path and almost reached the expected result. Functionality test is conducted to evaluate the developed system meet the expected goal. Two assumptions will be made to verify the working principle of the system, which are the Arduino coding and the feedback of system. Figure 7 shows the control mechanism of the system. The power to empower the retraction system is host PC and battery. The sensory system load cell is integrated with the motor driver as to generate an automatic rotation of the DC motor. Arduino Uno will be the microcontroller of the system. For the output, the rotation of the DC motor is activated based on the threshold displayed at the LCD screen. The development of microcontroller is shown in Figure 8. Meanwhile, Table 5 and Table 6 show the wiring between the electrical components. The tethered drone design is being improved with time as to maximize the performance of the station. The location of load cell is rearranged for every design. To add, brackets also have been redesigned with a bigger dimension as to minimize the strain that causes the bracket to bend and allow the load cell to measure the strain in a rigid condition. The prototype that been shown earlier is based on the final design. For final evaluation, we conducted testing to verify the proposed concept. There are three items that we focus on, which are the tension produced by the tether, the load cell feedback, and the movement of the shaft at the DC motor. The manipulated variable for this testing is the force produced by the tether. Different mass values are being used, of which can be assumed as the force produced by the drone itself. Two assumptions which represent for each condition, retraction and release, is made. For retraction condition, when retraction force is at or lower than upper preset threshold, it indicates the wire is in loosen mode. Thus, retraction process is activated. DC motor will rotate in clockwise. Stable condition is said that the load in the range of 50 grams from the upper threshold. For release condition, when retraction force is at or higher than upper preset threshold, it indicates the wire is in stretching mode. Release process is activated. DC motor will rotate in anti-clockwise rotation. Stable condition is said that the load in the range of 50 grams from the upper threshold. Table 7 and 8 show the result from the testing. The preset threshold is set in the coding of the Arduino and the actual threshold is shown when running the testing. The mode of motion is achieved and based on threshold mentioned, we will find the difference that produced. The difference is calculated and the percentage of error of the system is obtained. Finally, conclusion. In conclusion, the development of tethered drone station is conducted successfully as all the objective is fulfilled. The integrating between the load cell which play the role of sensor and Arduino as microcontroller has successfully developed a retraction system for the station. The final evaluation of the developed tethered drone station found that the design has fulfilled the expected predefined performance. The accuracy for the developed system, both in retraction and release condition, has an average error percentage of 1.85 and 1.07 respectively. For recommendation for future study, the load cell sensor should be calibrated with a series of repetition to acquire an average strain value. Next, to reduce the risk of cracking and failure, use a rigid material for critical parts of the station, such as the station base frame, the spool holder, and the tension guard. Run a stress simulation for fabrication to determine whether the part's performance can tolerate the load stress. Lastly, additional testing should be carried out to evaluate the system that been developed has a high accuracy percentage. With that, my presentation is coming to an end. Thank you for your attention.